Peterson's solution. Peterson's solution is a software-based solution for critical section problem. You can remember from the last lecture, critical section is the part of a program which tries to access the shared resources or shared data. And critical section problem is to design a set of protocols which ensure that race conditions will never arise among the processes. It is a two-process solution. Peterson's solution is applicable for only two processes. If there are more than two processes, Peterson's algorithm will not work. The processes share two variables, a turn variable of type integer and a flag array of type boolean. The variable turn indicates whose turn it is to enter the critical section. For example, if turn is equal to I, then process Pi is allowed to execute in its critical section. The flag array is used to indicate if a process is ready to enter the critical section. For example, if flag of I is true, this means process Pi is ready, or process Pi wants to execute its critical section. This is the algorithm for a typical process Pi. This algorithm is composed of four parts: entry section, critical section, exit section, and remainder section. Entry section contains the code that allows a process to enter its critical section. Critical section is the part of the process in which shared data is accessed and manipulated. Exit section, it indicates that a process has finished executing its critical section, and now the other processes which are waiting in the entry section, they can be allowed to execute their critical section. The rest of the process code is known as remainder section. Remainder section can be executed by the cooperating processes without any concurrency issues. In its entry section, a process will change its flag value to true. So process Pi will change its flag of I to true, indicating that process Pi wants to execute its critical section. Then it would change turn variable to value j. Why it would change turn variable to j instead of I? It sets turn to value j, thereby asserting that if other process wishes to enter its critical section, it can do so. This means process Pi assumes that process Pj also wants to execute its critical section, and process Pj is ready to enter its critical section. Hence, process Pi sets turn to value j so that process Pj could execute its critical section next. The last statement of the entry section is a while statement in which two conditions will be checked: the flag of j and turn. So process Pi will check that the flag of j as well as the turn is equal to j. If both conditions are true, this means process Pj wants to enter its critical section and it is the turn of process J. Hence, process Pi is not allowed to enter its critical section as long as these two conditions are true. If any of these two conditions become false, then process Pi will be allowed to execute its critical section. After process Pi has finished executing its critical section, it would change its flag value to false, thereby indicating that it has completed executing its critical section. Now the process Pj can execute its critical section if process Pj wants to enter its critical section. As you can remember that any solution to critical section problem must meet the three conditions: mutual exclusion condition, progress condition, and bounded waiting condition. The first of these, mutual exclusion condition, means only one process can execute critical section at any time. Suppose there are two processes, process Pi and process Pj. Initially, none of these processes want to enter their critical section. So the flag of I as well as the flag of J both are false. And turn can be set either to process I or to process J. We have set turn to I. Now suppose process Pi wants to enter its critical section. So process Pi will execute its entry section code. In entry section, it will change the flag of I to true and it would set turn variable to J. Hence, you can see the flag of I is true and turn has been set to value J. Now it would execute its while statement. Flag of J, this value is false, and turn is equal to J, this is true. Hence, false and true, the output would be false. Consequently, process Pi will be allowed to enter its critical section. So, process Pi will execute its critical section. Now, suppose process Pj, it has also expressed its wish to enter its critical section. So, it would change the flag of J to true and it would set turn to I, as you can see here. Now it would execute the while statement and it will find the flag of I, which is true, and turn is equal to I, this is also true. Hence it will stuck in this while loop because both conditions are true. This means process Pj must wait until the process Pi has completed executing its critical section. When the process Pi will finish executing its critical section, it would change the flag of I to false. As you can see here, the flag of I has become false. Now the process Pi will move to its remainder section, and because flag of I has become false, so process Pj will move to its critical section. While process Pj is executing its critical section, now the other process Pi cannot execute its critical section. To prove this, we suppose process Pi again wants to execute its critical section. So it has to execute the entry code first. It would change the flag of I to true and it would set turn to the value J. As you can see here, flag of I has become true and turn has been set to the value j. However, process P I will find flag of j which is true and turn is equal to j. Yes, it is equal to j. So both of these conditions are true, hence it must wait here at the while loop. Process Pi will not be allowed to execute its critical section because process Pj is already executing its critical section, and only one process can execute critical section at any time. Hence, mutual exclusion condition is observed in the Peterson solution. Let's talk about the next condition, progress condition. Progress means if no process is currently executing its critical section and one or more processes wish to enter their critical section, then only the processes not in their remainder section can participate in the decision, and the decision cannot be postponed indefinitely. This means if a process wants to enter its critical section and there are processes which are not in their critical section, then this process must not be blocked by those processes to enter its critical section. We suppose that process Pj is in its remainder section. In other words, process Pj doesn't want to execute its critical section. It is busy executing its remainder section. Hence, flag of j is false because process Pj has changed the flag value to false, then it jumped to the remainder section, and while it is executing remainder section, it should not block the other process Pi that wish to enter its critical section. It should not block this process entry into its critical section. In order to enter its critical section, process Pi should change the flag of I to true and it should set the turn to value j. As you can see here, the flag of I has become true and turn has been set to j. Process Pi will find the flag of j which is false and turn is equal to j which is true. False and true would result into false. Hence process Pi will be allowed to execute its critical section. After process Pi has finished its critical section, it would change the flag of I to false, as you can see here. Then it would jump to its remainder section. Suppose process Pi, which is executing its remainder section, it again wants to execute its critical section. So it must execute the entry section code again. It would change the flag of I to true and it would change turn to the value j. As you can see here, flag of I has become true and turn has been changed to the value j. Now it would check the conditions in the while loop, flag of j which is still false and turn is equal to j. Yes, it is true. False and true, the output would be false. Hence process Pi will be allowed entry in its critical section one more time. We can see that process Pi can execute its critical section as many times as it wants until the process Pj is not interested executing its critical section. The third condition is bounded wait. A bound must exist on the number of times that other processes are allowed to enter their critical sections. After a process has made a request to enter its critical section, and before that request is granted. Suppose both of these processes, Pi and Pj, they want to execute their critical section. So the both of these processes will change the flag value, the corresponding flag value to true. However, when they will execute the next statement of their entry section, which is the assignment to the turn variable, they will execute the corresponding turn statements concurrently. We suppose process Pj, it has first executed the turn statement. So it would change the turn to the value I. After this, process Pi, it will execute this assignment statement. So it would change the turn to the j. The previous value I will be replaced by this new value j, as you can see here. Now process Pi will check its while condition and process Pj will also check its while condition concurrently. So when process Pi will check its while condition, it will see flag of j, which is true, and turn is equal to j, which is also true. So it will stuck in this while loop. However, when process Pj will execute its while statement, it will see flag of I, which is true, and turn is equal to I, which is false because turn has been set to j. So it will be allowed entry in its critical section. After process Pj has executed its critical section, it would change the flag of j to false and it will jump to its remainder section. Now suppose process Pj again wants to enter its critical section, so it will execute the entry section code one more time. It would change the flag of j to true and it will set turn to I. As you can see here, flag of j has become true and turn has been set to I. Now it will see these two conditions in the while loop of the entry section, flag of I, which is true, and turn is equal to I, which is also true. So it will stuck here. It will not be allowed entry in its critical section because there is a bound. There is a limit that when this process Pi has requested entry in its critical section, after that how many times process Pj can execute its critical section before the request of process Pi has been granted. Now when process Pj has been stuck in its while loop, process Pi will find flag of j, which is true, and turn is equal to j. This condition is false, hence it will be allowed entry in its critical section. After process Pi has executed its critical section, it would change the flag of I to false and it will execute its remainder section. Now suppose process Pi again wants to execute its critical section, so it would change the flag of I to true. As you can see here, flag of I is true and it would set turn is equal to j. However, it would stuck at this while loop because flag of j is true and turn is equal to j. This is also true. So both conditions are true. It will not be allowed entry in its critical section. Why? Because now it is the turn of the process Pj. Now the flag of I is true and turn is equal to I, which is false. So process Pj will now be allowed to enter its critical section. Hence, from this example, we observe that the processes are alternating their turns. First, it was the process Pj, which was allowed entry in its critical section, while the process Pi was waiting in its entry section. Then process Pi was allowed entry in its critical section, and again then it was the process Pj which will be allowed entry in its critical section. So the processes are changing, or you can say they are alternating their turns. Peterson's solution preserves all the three conditions of a critical section problem. Mutual exclusion is preserved as only one process is allowed to enter its critical section at a time. Progress requirement is also satisfied because a process outside the critical section doesn't block other processes from entering the critical section. Bounded waiting requirement is also satisfied as every process gets a fair chance. We have seen in the example that processes are alternating their turns. A process has to wait at most one entry of the other process in its critical section before the request of the waiting process is granted. As far as the limitations of Peterson solutions are concerned, it is only two process solution. The solution is limited to two processes. If there are more than two processes, Peterson's algorithm will not work. And secondly, it involves busy waiting. Busy waiting means when a process stucks at the while loop. When both of these conditions in the while loop they become true, the process must wait. It will keep looping in this while statement until one of these two conditions become false. And the time when the process has been looping in this while statement, this is known as busy waiting. During this time, process cannot move to its critical section. It must wait at this while loop.